Think about welding for a second. When it goes perfectly, you've essentially created, well, a new piece of continuous metal. Seamless.
Right. That's the goal. But, in reality, there are always little hiccups, things that aren't quite ideal in that perfect fusion.
Deviations?
Exactly. We see deviations. And in the welding world, we call those imperfections. Now, here's a crucial point, though. Not every single imperfection is a red flag. Not automatically.
Okay, so where do we draw the line then? When does a little become a real problem?
That's where the concept of a defect comes in. A defect is an imperfection that's actually unacceptable. It's something that weakens the weld or stops it from doing what it's supposed to do.
Right.
Imagine, a tiny bit of extra weld metal on top. That's an imperfection, maybe visually not great, but often harmless.
Okay.
But a hairline crack snaking through the weld, that's almost certainly a defect, no question.
Right, so it's really about whether it compromises the integrity or the function. Now, these imperfections, they don't all look the same, do they? Are there some main ways we categorize them?
Absolutely. Yeah, when we look at fusion welds, we generally see 6 main groups based on their geometry, their appearance.
6 groups, okay.
First, you have cracks, which are basically ruptures or breaks in the solid metal.
Okay.
Then there are cavities, think voids, holes inside the weld.
Got it.
We also encounter solid inclusions, which are bits of foreign material trapped within the weld metal itself.
Cracks, cavities, solid inclusions. What are the other categories?
So next we have issues with how well the weld metal has actually bonded to the original metal or even to previous layers of weld. That's lack of fusion.
Ah, okay.
And then there's whether the weld metal has penetrated deeply enough into the joint. That's lack of penetration, similar but distinct.
Right.
We also see imperfections in the overall shape and size of the weld bead itself. Is it too big, too small, the wrong shape?
Makes sense.
And finally, there's a sort of catch-all group, miscellaneous imperfections, for anything else that doesn't quite fit neatly into those first 5.
Okay, that's a good overview. Cracks sound particularly concerning, though. Is there a reason they're generally viewed as more serious than, say, a cavity?
Definitely. It's all down to the shape, really.
Yeah.
Stress concentration.
How so?
A crack has a very sharp tip, and that sharp point acts as a stress concentrator. Think of it like this. It's much easier to tear a piece of fabric if you make a small nick in it first, right?
Absolutely.
The crack tip is exactly like that initial nick, but in the weld. It magnifies the stress right at that point.
That makes perfect sense. So when we talk about cracks, are there different types we need to be aware of based on how they look or where they are?
Yes, several ways to classify them. We see them oriented in various ways. You can have cracks running lengthwise along the weld longitudinal.
Okay.
Or cross it transverse. Some radiate outwards from a central point, like spokes on a wheel.
Right.
And others branch out, like a tree. Then you have crater cracks, which are a bit special because they only occur right at the very end of a weld bead, in the weld metal itself.
Ah, where you stop welding.
Exactly. And these cracks, they can appear in different parts of the welded assembly too, not just in the weld bead itself.
Right. Well,
They can be right in the weld metal, sure,
yeah.
but also in that heat affected zone, the HAZ, the area of the original metal that got hot but didn't actually melt. Or they can even form further out in the original parent metal, away from the immediate weld area.
Now, I know cracks can form at different temperatures, too. We often hear about hot cracks and cold cracks. What's the difference there? What's going on?
Precisely. That's a key distinction based on when they form. Hot cracks form when the weld is still at a high temperature, either as it's solidifying or very shortly after.
Okay, during or just after welding?
Yeah. And within hot cracking, we generally distinguish between solidification cracks and liquation cracks.
Okay, so solidification cracks, when and where do those typically happen?
Solidification cracks occur right in the weld metal itself as it's transitioning from liquid to solid. You often find them running down the center line of the weld.
Center line, right.
These can be triggered by things like too much carbon or other impurities in the metal. Stuff like sulfur and phosphorus are classic culprits.
Why impurities?
Well, imagine those impurities being pushed ahead of the solidifying metal grains. They end up concentrated at the boundaries between the grains as it freezes, creating these weak, still liquid films that then crack under shrinkage stress.
Ah, I see.
Also, if you have a really narrow and deep weld bead shape, that can be prone to it, Or if the heat flow is interrupted, like when you stop and restart welding, those interruptions can cause issues.
Okay. And liquation cracks, you said those are different.
Liquation cracks, yeah, they tend to appear in that heat-affected zone, the HAZ, very close to the fusion line where the weld metal melted and joined with the original metal.
In the parent metal, but right next door.
Exactly. In this zone, the high temperatures can actually cause low melting point constituents that are already present at the grain boundaries in the parent metal to melt slightly or liquate. Then, as the weld cools and shrinks, these thin, resolidified liquid films are weak spots, and they can crack under the stress.
So hot cracks are pretty immediate then. What about those precipitation-induced cracks you sometimes hear about? Reheat cracks.
Yeah, those are a bit different. You typically see them in specific types of steel, like creep-resisting steels used in high-temperature applications.
Okay.
These cracks, sometimes called reheat cracks, don't form during the initial welding process itself. They appear later, often when the welded part is reheated, maybe during post-weld heat treatment, or even during its service life at elevated temperatures. It's related to precipitates forming and causing embrittlement.
Right, so a delayed reaction triggered by heat later on. Now, cold cracks, they sound particularly problematic. I'm often linked to hydrogen, right? What's the mechanism there?
Cold cracks, or hydrogen-induced cracks, are definitely a major concern in steel welding. They form in the heat-affected zone, typically, but they don't show up right away. That's the tricky part.
Delayed cracking.
Exactly. They can take hours, even days, to appear after the welding is finished, which is why they're also known as delayed cracking. You might also hear them called underbead cracking or toe cracking, depending on their specific location relative to the weld.
And hydrogen is the key player here, I understand. How does that cause the cracking? It seems counterintuitive for a gas to cause cracks in solid steel.
It does, doesn't it? But yeah, hydrogen is critical. For hydrogen-induced cracking to happen, you really need a specific combination of 4 factors to be present simultaneously.
4 factors. Okay, what are they?
First, you need a significant amount of hydrogen dissolved in the weld area. We measure it in milliliters per 100 grams of weld metal, and you generally need above about 15 milliliter to 100 grams.
Okay, high hydrogen level.
Second, you need high tensile stress acting on the joint. This could be residual stress from the welding itself or applied stress. Usually needs to be over half the yield strength of the material.
High stress. Got it.
Third, you need a relatively low temperature. It typically occurs below about 300 degrees Celsius, often closer to room temperature. That's why it's cold cracking.
Low temperature. Makes sense.
And fourth, you need a microstructure in the heat-affected zone that's susceptible to cracking. This often means a hard, brittle microstructure, frequently indicated by a high hardness value, say, over 400 HV.
Susceptible microstructure. So hydrogen, stress, low temp, and the right structure.
Bingo. If any one of those isn't present or is below the critical level, the cracking generally won't occur.
So if you can control any one of those 4 things, you can prevent it. That gives you levers to pull.
Precisely. And that gives us several strategies for prevention. It's all about managing those 4 factors.
Like what? What are the common approaches?
Well, one common method is preheating the metal before welding.
Heating it up first.
Yeah. This slows down the cooling rate after welding. Slower cooling helps avoid forming those hard, susceptible microstructures. Plus, it gives the hydrogen more time to diffuse out of the steel before it gets trapped.
Okay, preheat helps with microstructure and hydrogen escape.
Right. And maintaining a specific minimum temperature between weld passes the inner pass temperature has a similar benefit. Keeps things warm, lets hydrogen move.
What about after the welding is done? Can you do anything then?
Definitely. Post-heating immediately after welding, just holding it at a certain temperature for a period, can also help drive out any remaining hydrogen before it cools down too much.
Okay.
And a more thorough post-weld heat treatment, or PWHT, can be very effective. That not only drives out hydrogen, but also reduces residual stresses and tempers the microstructure, making it less brittle and less prone to cracking.
So heat treatment is key. It sounds like minimizing the amount of hydrogen introduced in the first place is crucial too. How do you achieve that? Where does the hydrogen come from?
Absolutely. Source control is vital. Hydrogen can come from moisture in welding consumables like stick electrodes or fluxes, or from contaminants like oil, grease, rust, or even paint on the joint surfaces. Water vapor in the atmosphere or in shielding gases is another source.
So keep everything clean and dry.
That's a huge part of it. Using low hydrogen consumables is critical. For stick welding, that means using basic coated electrodes, which need to be properly stored and sometimes baked before use to keep them dry.
Right, those special handling procedures for low hydrogen rods.
Exactly. Processes like TIG welding are inherently lower in hydrogen than, say, stick welding with cellulose electrodes. So process selection matters.
Okay.
Also, ensuring your shielding gases are dry, especially for MIG, MAG, and TIG, is important. Checking for leaks in gas lines. And thorough cleaning of the joint, grinding away rust, scale, any contamination before you weld.
Makes sense. Any other practical steps, techniques maybe?
Yeah, multi-pass welding techniques can actually help. Each subsequent pass has a sort of heat-treating effect on the layer below it, which can refine the microstructure and give hydrogen more opportunities to escape.
Interesting.
Techniques like temper bead welding are specifically designed to refine that critical HAZ microstructure. Sometimes using filler metals like austenitic stainless steel or nickel-based alloys can be a solution, even when welding certain steels.
Why is that?
Because those types of weld metals don't form the hard, brittle microstructures as readily, and they can actually hold more hydrogen in solution, allowing it to diffuse away more harmlessly over time.
Ah, okay.
And finally, anything you can do to minimize residual stresses through joint design, sequencing, or restraint control, and creating a smooth weld profile without sharp notches or undercut where stress can concentrate will also help reduce the risk.
Wow, that's a really comprehensive set of strategies for tackling hydrogen cracking. Now, you mentioned one more type of crack that seems quite different, lamellar tearing. You said it looks terraced.
Yes, lamellar tearing is quite unique. It's really specific to rolled steel plates, particularly in thicker sections. The key visual clue is its characteristic stepped or terraced appearance within the crack surface. It looks different from other cracks.
What's the underlying cause of that specific look? Why terraced?
It happens in certain joint configurations, like T-joints or corner joints, where the welding forces cause the plate to contract, pulling it in the through thickness direction, basically, perpendicular to the rolled surface of the plate.
Okay, pulling through the thickness.
Now, rolled steel often contains microscopic, flat, non-metallic inclusions, things like manganese sulfides that get flattened and elongated during the rolling process, so they end up oriented parallel to the surface of the plate.
Like tiny pancakes inside the steel.
Kind of, yeah. When that through-thickness stress from welding contraction occurs, it pulls directly on these weak, planar inclusions. They separate or decohere first, forming the flat parts of the steps, the terraces. Then the material between these separated inclusions fails, usually by a ductile shearing mechanism, creating the vertical parts of the steps that link the terraces together. That combination gives you the characteristic stepped look.
So it's the rolling process creating those weak planes and then the stress direction pulling them apart.
Yeah.
How do you prevent lamellar tearing then?
The most effective way is to address the material susceptibility. You can specify cleaner steels that have guaranteed properties in that through thickness direction. These are often designated as Z-grade steels. They have much lower inclusion content.
Use better steel, essentially.
Essentially, yes. Beyond the material, optimizing the joint design is crucial. Try to avoid details that put high tensile stress directly through the thickness of susceptible plates.
Okay.
Carefully controlling the restraint on the parts being welded, and planning the welding sequence strategically, maybe, using buttering layers on the play surface first, can all significantly reduce the risk as well.
Okay, we've covered cracks in quite a bit of depth there. Let's move on to the next category you mentioned. Cavities. These are essentially the holes or voids within the weld metal, right? Like little bubbles.
Exactly. That's a good way to think of it. And the most common type of cavity by far is a gas pore. These are typically round or nearly round voids formed by gas that gets trapped as the weld metal solidifies.
And these pores, they can show up in different ways, I imagine, not just single bubbles.
Right. You might see isolated pores just scattered randomly throughout the weld, or they can be fairly evenly distributed, which we call uniformly distributed porosity. Sometimes they cluster together in one specific area or even line up in a row, which we call linear porosity. That often follows the boundary between weld passes.
Linear porosity, okay.
If a pore gets elongated, almost like a tiny tube running through the weld, we refer to that as a wormhole. It's a specific type of gas cavity.
Wormhole, got it.
And if a gas pore actually breaks through the surface of the weld, that's simply called surface porosity. You can see it on the outside.
So what's the source of all this trapped gas? Where does it come from?
Well, several things can contribute. A major one, especially with stick electrodes or flux cord wires or submerged arc fluxes, is moisture. If consumables absorb moisture from the air, that water breaks down in the intense heat of the arc and releases hydrogen gas.
Hydrogen again.
Yep. Hydrogen loves to cause problems. Similarly, any contamination on the surfaces you're welding, grease, oil, paint, cutting fluids, even just rust with trapped moisture, can vaporize in the arc and get trapped as gas pores.
So cleanliness is key, again.
Absolutely. Clean and dry. Air can also get drawn into the shielding gas envelope in processes like MIG, MAG, and TIG if there are leaks in the gas hoses, loose connections, or if the gas flow rate isn't right.
Too much or too little flow?
Either can be bad. Too little flow doesn't provide enough protection. Too much flow can actually create turbulence around the nozzle, pulling air into the shield.
Okay, that makes sense. Keep things clean, dry, and ensure good gas shielding. What else causes porosity?
Sometimes the welding consumables themselves, or even the parent metal, might not contain enough deoxidizers. These are elements like silicon and manganese that are added specifically to react with oxygen and nitrogen that might get into the weld pool, tying them up as harmless slag instead of letting them form gas bubbles.
The chemistry matters.
It does. Also, using too high an arc voltage or too long an arc length can make the arc less stable and increase the chance of picking up atmospheric gases. Certain surface treatments on the metal, like some types of primer paint or galvanizing, can release gases when heated by the welding arc if not properly removed or accounted for.
Right. So it really emphasizes proper preparation, correct machine settings, using good quality dry consumables, and just good technique overall. Now, you mentioned wormholes specifically. How are those distinct from just regular round gas pores? What makes them tunnel like that?
Wormholes are definitely a more severe form of gas porosity. They're those elongated, sometimes branched tubular cavities. They're also caused by trapped gas, but the key difference is how they form. They tend to form as the gas tries to escape but gets trapped between the microscopic branches of the solidifying metal crystals called dendrites.
Trapped between the solidifying structure.
Exactly. This progressive trapping of the escaping gas can sometimes create a pattern on a radiograph, an X-ray image, that looks a bit like a herringbone pattern.
What causes wormholes specifically? Is it just really bad contamination?
Often, yes. Gross surface contamination is a common cause. Also, welding over surfaces that have internal laminations or layers within the steel can trap gases. Even having tight crevices in the joint geometry itself can sometimes trap gases and lead to wormhole formation during solidification.
Okay. And surface porosity is simply when any of these gas pores break through to the outer surface of the weld.
Exactly. The underlying causes are often the same as for the internal, uniformly distributed porosity, dampness, contamination, shielding gas issues, etc. But you might also see more surface porosity specifically if the flux used in certain processes, like stick or flux cord, isn't providing enough protective cover to the molten metal surface. Also, if there's a high sulfur content in the steel you're welding, which you sometimes find in free machining grades that can increase surface tension effects and make surface porosity more likely. And again, any disruption or loss of the shielding gas due to things like drafts, moving the torch too quickly, or holding too long an arc, or having the wrong gas flow rate can lead to pores forming right at the surface.
Gotcha. Lastly, in the cavity category, we have crater pipe. What's that all about? Sounds different from gas.
It is different. A crater pipe isn't caused by trapped gas. It's a shrinkage cavity. It forms specifically at the very end of a weld bead in the little depression or crater left when you extinguish the arc.
Why does it form there?
As that final bit of molten weld pool cools and solidifies, it shrinks, just like most metals do when they freeze. If the welder doesn't properly manage the end of the weld, that shrinkage can pull the metal inwards, leaving a small depression or even a distinct pipe-like cavity right in the center of the crater.
Is it more common in certain processes?
It can happen in many processes, but it's perhaps most noticeable and potentially problematic in TIG welding, where the heat input can be quite focused and the welder has direct control over stopping the arc.
So it's often down to technique.
It often is, yeah. It can be a sign of less experienced welders who might just break the arc abruptly while using a high current without taking steps to fill the crater properly. TIG welding actually has a specific technique called crater filling.
Crater filling?
Yeah, where the welder gradually reduces the welding current, maybe adding a dab of filler wire right at the end, allowing the crater to solidify smoothly and completely without forming that shrinkage pipe. Some machines even have automatic crater fill functions built in.
Interesting. Okay, cavities covered. Let's move on to solid inclusions.
Yeah.
You said these are bits of foreign material that end up trapped inside the weld metal. What are the main types we see there?
Right, foreign stuff that shouldn't be there. The main types are slag inclusions, flux inclusions, oxide inclusions, and sometimes, specifically in TIG welding, tungsten inclusions.
Okay, let's start with slag inclusions. What exactly is slag, And how does it get trapped?
Slag is the non-metallic byproduct that forms from the flux used in certain welding processes like stick welding, SMAW, submerged arc welding, SCSIW, and flex cord arc welding, FCAW. It melts during welding and forms a protective layer on top of the molten weld pool as it solidifies. Its job is partly to protect the hot metal from the atmosphere.
So it's supposed to be there, but on top.
Exactly. Slag inclusions occur when this slag, which should normally just sit on top and be chipped or brushed off after cooling, gets trapped within the weld metal itself or between weld passes in a multi-pass weld. They usually look like irregular shapes on a radiograph.
How does that happen? How does it get trapped inside?
Several ways. A very common cause in multi-pass welds is simply incomplete cleaning between passes. If the slag from a previous weld pass isn't completely removed before the next pass is deposited on top, it just gets welded over and trapped.
So thorough inter-run cleaning is absolutely key.
Crucial. Also, the welding technique matters. If the welder lets the molten slag run ahead of the arc, especially in certain positions, the arc might not be able to melt through it properly and it gets trapped underneath the weld bead.
Okay.
And sometimes, if there are irregularities or deep grooves or undercuts on the work surface or in the previous weld bead, slag can become physically trapped in those features.
Right, so good cleaning, good technique, and a smooth surface help avoid them. What about flux inclusions? How are they different from slag?
They're very similar, and sometimes the terms are used interchangeably, but technically, flux inclusions refer specifically to trapped particles of the original unmelted flux material, rather than the glassy slag that forms after melting.
Okay. Unmelted flux.
Yeah. This can happen in flux-associated processes like stick, submerged arc, and flux cord. For instance, if the flux coating on a stick electrode is damaged or chipped, pieces might fall into the weld pool without melting properly. Or, in submerged arc welding, if the granular flux doesn't melt completely due to incorrect settings or technique, some of those unfused granules can get incorporated into the weld metal.
So proper handling of consumables and correct parameters are important there. What about oxide inclusions?
Oxide inclusions form when oxides think heavy mill scale, which is iron oxide formed during steel production, or just plain rust that's present on the surface of the parent metal, get mixed into the weld pool during welding.
So surface contamination again.
Exactly. This really highlights, again, how important it is to properly prepare the joint by thoroughly cleaning or grinding away any of this surface scale or rust before you start welding. If you weld over it, bits of it can get trapped.
Makes sense.
In aluminum alloys, you can also get a specific type of oxide inclusion, sometimes called puckering. The aluminum oxide layer on the surface is very tough and has a high melting point. If the shielding gas isn't adequate or there's excessive turbulence in the weld pool, this oxide film can get folded into the molten aluminum and trapped.
Okay. Special case for aluminum. Finally, tungsten inclusions. I know tungsten electrodes are used in TIG welding, but they're not supposed to actually become part of the weld, are they? They should stay separate.
Exactly right. Tungsten inclusions are small particles of the non-consumable tungsten electrode that break off and end up embedded in the weld metal. Because tungsten is a very dense material compared to steel or aluminum, these show up as distinct bright white spots on radiographic inspections, X-rays.
How does that happen? How does the tungsten get into the weld?
Oh, there are quite a few ways, unfortunately. It often comes down to technique and setup in TIG. The most direct way is if the welder accidentally touches the tip of the tungsten electrode directly into the molten weld pool.
Tipping the tungsten.
Yeah, that'll usually transfer some tungsten.
Yeah.
Similarly, if the filler metal rod accidentally touches the hot electrode tip before melting into the pool, it can pick up tungsten and carry it into the weld. Even weld spatter landing back onto the hot electrode can contaminate it and lead to inclusions.
Okay, so careful manipulation is key. Any other causes?
Yes. Exceeding the recommended current range for a given electrode size can cause the tip to overheat, melt, and drop off into the weld.
Too much power.
Right. Extending the electrode too far out from the gas nozzle, the stick out, can lead to overheating because it's not getting enough shielding gas cooling. Not properly tightening the collet that holds the electrode can cause poor electrical contact, overheating, and potential erosion.
Setup issues.
Definitely. Insufficient shielding gas flow or having drafts blow the shielding gas away can also cause the electrode tip to oxidize and become brittle, making it more likely to break off. Even using an electrode that has small cracks or splits in it can be a source. And it's absolutely crucial to use the correct type of shielding gas for TIG, usually pure argon or an argon-helium mix. Using gases that contain oxygen or carbon dioxide, like you might for MIG welding steel, will rapidly destroy the tungsten electrode.
Wow, that's quite a list of potential pitfalls for tungsten inclusions. It really underscores the importance of careful technique, correct setup, and using the right consumables in TIG welding. Okay, let's switch gears now and talk about when the weld metal doesn't quite do its main job of joining things together properly. That brings us to lack of fusion and lack of penetration. First off, what exactly do we mean by lack of fusion?
Lack of fusion essentially means just that the molten weld metal hasn't properly bonded or joined with the adjacent material. There's no solid metallic continuity. It's a failure to create that bond.
Where can this failure happen?
It can happen between the weld metal and the parent metal surface, or it can happen between adjacent weld beads in a multi-pass weld.
Okay, and there are different terms depending on where it occurs in the joint.
Yes, exactly. We talk about lack of sidewall fusion when the weld metal doesn't fuse correctly to the sides of the joint preparation where it meets the original parent metal.
Okay, on the sides.
Then there's lack of inter-run fusion, which happens between the individual weld beads or layers in a multi-pass weld. The new layer doesn't properly melt and fuse into the one underneath or beside it.
Between the runs.
And finally, lack of root fusion is when the weld metal fails to fuse properly with the parent metal at the very base or root of the weld joint, right at the bottom.
Got it. So what are some of the common reasons for lack of sidewall fusion? Why wouldn't it stick to the sides?
Often it comes down to insufficient heat input. Basically, the weld pool isn't hot or fluid enough to properly melt the adjacent sidewall material and fuse with it.
Not hot enough.
Right. This can be caused by using too low a welding current or voltage for the material thickness and joint type, or by welding too quickly, not allowing enough time for the heat to transfer.
Okay.
Sometimes, particularly in downhill welding or with incorrect technique, the molten weld metal can actually flow ahead of the arc, kind of insulating the sidewall and preventing the arc from directly impinging on it and melting it.
The metal gets in the way of the arc.
Exactly. Surface contaminants like oxides or heavy mill scale that haven't been completely removed from the sidewalls can also act as a physical barrier to fusion.
Cleaning again.
Always. And in certain welding modes, like the short-circuiting transfer mode in MIG-MAG welding, having excessive inductance in the welding power source circuit can sometimes lead to a colder, less fluid weld pool that's more prone to lack of sidewall fusion.
Okay. And what about lack of inter-run fusion between those passes in a multi-pass weld? Same reasons?
Often similar reasons, yes. Insufficient heat input, low current, or voltage can certainly be a factor. Traveling too quickly on the subsequent pass doesn't give it enough time to properly melt into the preceding bead.
Too fast.
Yeah, and sometimes it's simply about bead placement. If the welder doesn't position the subsequent weld beads accurately so they adequately overlap and melt into the previous ones, you'll get voids or unfused areas between them. Welder skill and attention are key here.
So technique matters a lot.
Definitely. Lack of inter-run fusion can be particularly problematic because it creates these little crevices or laps between the beads, which are perfect places for slag to get trapped in processes where slag is produced.
One imperfection leading to another.
It happens.
Yeah.
Now, what about lack of root fusion? What makes it difficult to get proper fusion right at the very bottom of the weld joint? That seems like a critical spot. It is critical, and it can be tricky. Again, similar to sidewall fusion, insufficient heat input is a frequent culprit. Not enough energy getting right down into the root.
Not enough heat.
Excessive inductance in mag welding, as mentioned before, can also hinder root fusion specifically. If you're using a stick electrode that's simply too large in diameter for the joint geometry, you might not be able to direct the arc precisely enough into that narrow root area to achieve fusion.
Wrong electrode size.
Right. Welding position matters too. Welding in the vertical down progression can sometimes make it harder to achieve good root fusion compared to vertical up because gravity is working against you, pulling the molten metal away from the root. And sometimes the way the joint is prepared is the issue. If the root face the little flat land at the bottom of the bevel is too wide, or if the root gap, the space between the two pieces, is too narrow, it can physically prevent the weld metal from reaching and fusing properly with both root surfaces.
Joint geometry itself.
Absolutely. Incorrect electrode angle or manipulation by the welder not getting the arc pointed right into the root, and even if the two pieces being joined are significantly misaligned, that can all contribute to a lack of root fusion.
So it really sounds like getting the heat input just right, meticulous joint preparation and cleaning and having good, precise welding technique are absolutely critical for preventing all these types of fusion issues. Now let's move on to lack of penetration. How is that different from lack of root fusion? They sound similar.
They are closely related, especially at the root, but there's a subtle difference in definition. Lack of fusion is about the bond not forming. Lack of penetration is about the depth to which the weld metal extends into the joint.
Depth versus bond.
Exactly. Lack of penetration is essentially the difference between the intended or nominal depth of the weld, as might be specified in the welding procedure, and the actual depth that was achieved. A common term you'll hear is incomplete penetration, or IP, which simply means the weld didn't go as deep into the joint as it was supposed to.
Okay. And what are the common causes of incomplete penetration? Why doesn't the weld go deep enough?
Well, many of the causes overlap significantly with lack of root fusion, because that's where penetration is often most critical. A root face that's too wide or a root gap that's too narrow can physically block the weld pool from penetrating deeply enough.
Preparation again.
Yep. Insufficient heat input is a major factor here as well. Not using enough welding current or voltage or welding too quickly just doesn't drive the heat deep into the material.
Not enough energy.
Excessive inductance in mag welding can limit the penetration depth. Using a stick electrode that's too large for the application can result in a wider, shallower, less penetrating arc profile.
Electrode choice.
Right. And again, welding in the vertical down progression tends to produce shallower penetration than vertical up. It's important to remember, though, that in some less critical applications, a partial penetration weld, where the weld doesn't go all the way through the joint thickness, might actually be intentionally specified in the engineering design. It's not always a defect if it meets the design requirement.
Good point. Sometimes it's deliberate. Now, you also hear the term incomplete root penetration. Is that essentially the same thing as lack of root fusion or incomplete penetration at the root?
It's very closely related to both, yeah. Incomplete root penetration specifically means that the weld metal hasn't fully extended through the thickness of the joint right at the root. Typically in this case, both of the root fusion faces, the bottom edges of the joint preparation, are not melted and joined by the weld metal.
So you can see the original edges, maybe?
Yeah, often, yes. If you were to look at the back side, the root side of the weld, you would likely see a lack of weld metal there, and potentially the original square edges of the root face still visible and unfused. The causes and the methods for preventing it are generally the same as for lack of root fusion, proper prep, sufficient heat input, correct technique.
Okay, got it. We're making good progress through these categories. Next up, imperfect shape and dimensions. This sounds like it's about the overall geometry of the weld bead itself. Is it the right size and shape?
Exactly. This category covers deviations in the weld's external profile or its overall dimensions compared to what's considered ideal or specified.
Let's start with undercut. I see that one mentioned quite frequently. What is it exactly?
Undercut is an irregular groove or notch that forms in the parent metal, or sometimes in a previously deposited weld bead, right at the toe of the weld, the line where the weld metal meets the base material.
Like a little ditch dug out next to the weld.
That's a good description, yeah. It's characterized by its depth, its length along the weld toe, and how sharp the transition into the groove is. A sharp undercut can be a significant stress riser.
Right. What causes that little bite out of the base metal at the edge of the weld? Why does it happen?
Often it's related to heat input and technique. Using too high a welding current can cause the edges of the weld pool to melt excessively into the parent metal, and then when the weld metal solidifies and shrinks, it pulls away slightly, leaving that groove. This is especially true when you're welding near a free edge of the material, where the heat can build up more easily.
Too hot at the edges.
Right. Welding too quickly can also sometimes cause undercut, paradoxically. Also, incorrect technique, particularly in positional welding, like the horizontal-vertical 2F position, if the welder dwells too long at the top edge, can lead to undercut there. Excessive weaving of the welding electrode back and forth, using an incorrect electrode angle, or even using the wrong type of shielding gas in MIG-MAG welding can all contribute.
Lots of potential causes.
It's worth noting, too, that if you have to repair undercut by adding a small bead of weld metal to fill the groove, you need to be careful. The heat input of that small repair weld, if it cools very quickly, can actually increase the hardness of the parent metal right in that sensitive toe area, potentially making it more susceptible to hydrogen cracking later on.
That's a good reminder. Be cautious, even when trying to correct an imperfection. You might introduce another problem, What about the opposite issue, excess weld metal? Sometimes you see a weld that's really built up, very convex, bulging out.
Right. Excess weld metal refers to depositing more weld material than is actually required by the joint design or specification. This results in an overly convex shape in fillet welds, or weld reinforcement, the part sitting above the surface, in butt welds that exceeds the limits allowed by the relevant welding standard or code.
So it's only an imperfection if it exceeds the specified limits.
Exactly. A certain amount of convexity or reinforcement is usually acceptable, even desirable sometimes. But when it goes beyond the allowable tolerances, then it becomes an imperfection.
What causes you to deposit too much metal?
Common causes include using too much arc energy, maybe too high a current or voltage, or too slow a travel speed. Having a joint preparation with very shallow bevel angles that simply doesn't require much filler metal can lead to overfilling if the welder isn't careful. Poor manipulation or technique by the welder, using an electrode size that's too large for the joint, or even using an incorrect welding polarity in some processes can all contribute to piling up too much metal.
It seems intuitive that more metal might be stronger, but is that always the case?
Not necessarily, no. It's interesting, while you might think that more weld metal means a stronger weld, in many cases excessive reinforcement in a butt joint doesn't actually increase the static strength significantly. What it can do, however, is create sharper transitions at the weld toes, acting as stress concentrations, much like undercut. This can be detrimental, particularly under fatigue loading conditions, where cracks can initiate at those toes.
Right, so more isn't always better. Smooth transitions are often more important. Now, what about the flip side on the root excess penetration? Sometimes you see the weld bulging out too much on the back side of the joint.
Yes, excess penetration, sometimes called over-penetration, is when the weld bead on the root side of the joint protrudes too far beyond the surface, exceeding the acceptable limits defined in the welding standard. A little bit of root reinforcement is usually desired to ensure full fusion, but too much can be a problem.
What causes it to push through too much?
Again, often related to heat input. Using too high a heat input for the joint preparation and material thickness is a common cause. Incorrect joint preparation itself can contribute, for instance, having an excessively large root gap, or grinding the root faces down so they're too thin, feather edge.
Preparation issues again.
Yes. Using an electrode type or size that isn't appropriate for the welding position, for example, using a hot electrode designed for flat welding in an overhead position, can make it hard to control the pool. And sometimes it's simply down to a lack of welder skill in controlling the molten pool, especially in tricky situations like welding pipe roots where you're constantly changing position.
It sounds like getting that consistent, just right penetration bead takes real skill.
It absolutely does. That's why techniques like using backing bars, strips of metal placed on the backside of the joint, are sometimes used. They help support the molten pool and control the amount of root penetration, making it easier to achieve consistency.
Okay. Overlap is another one that seems related to the shape of the weld at its edges, maybe similar to undercut.
It's related to the edge, yes, but it's kind of the opposite of undercut. Overlap occurs when the molten weld metal flows out onto the surface of the parent metal at the toe of the weld, but doesn't actually fuse with it. It just sort of sits on top.
Like cold lap-in casting.
Similar concept, yeah. It creates a notch, similar to undercut, but it's formed by the weld metal itself lying on the base metal without bonding.
What causes that?
Often it's due to poor manipulation of the welding electrode or torch, maybe incorrect angle or movement. Using too high a heat input combined with too slow a travel speed, particularly in fillet welds, can create a very large fluid weld pool that slumps and flows out without fusing at the edges.
Too much heat, too slow.
Incorrect positioning of the workpiece during welding can also contribute, letting gravity pull the pool where it shouldn't go. And sometimes using a welding electrode with a coating that produces a very fluid slag or weld metal can make overlap more likely if the technique isn't adjusted accordingly.
Okay.
In fillet welds made in the horizontal-vertical 2F position, you can sometimes see a combination defect where you get overlap at the bottom toe of the weld and undercut at the top toe. This is often referred to as sagging. The large weld pool slumps downwards due to gravity, causing both problems.
Sagging, right? Now we're moving into issues that seem more about how the different parts of the whole welded assembly line up with each other. Let's talk about linear misalignment first. What's that?
Linear misalignment, sometimes called offset, is when the two pieces being welded are intended to be in the same plane, maybe edge to edge in a butt joint, but they end up being parallel to each other but offset, so their surfaces aren't flush. One piece is higher than the other.
So they're not lined up correctly side to side.
Exactly. Now, this isn't technically a weld imperfection itself, but rather a problem with how the structure was prepared or assembled before or during welding. It's a fit-up issue.
What causes it? Just sloppy assembly.
It can be inaccuracies during the fitting and tack welding stage, yes. Or it can be caused by distortion that occurs during welding if the parts aren't properly clamped or if the welding sequence isn't managed well. Sometimes the original parts themselves, like rolled steel sections, might have some inherent out-of-flatness that contributes.
Why is it considered a problem if the weld itself is okay?
Because even a small amount of linear misalignment can significantly change how stresses are distributed across the joint. It introduces additional bending stresses that probably weren't accounted for in the original design calculations, which rely on the parts being aligned. This can seriously reduce the strength or fatigue life of the joint.
Okay. It affects the structural behavior. And angular distortion, is that similar?
Yes, angular distortion or angular misalignment is also a problem with alignment, but in this case, the two pieces being welded end up not being parallel to each other, or they're not at the intended angle relative to each other after welding is complete. Think of two plates in a T-joint that are supposed to be at 90 degrees, but end up at 85 or 95 degrees.
So the angle is wrong.
Right. The causes and the methods for minimizing it are generally the same as for linear misalignment, careful and accurate assembly, proper clamping or fixturing to maintain the correct angle during welding, and controlling the welding sequence and heat input to minimize the shrinkage forces that tend to pull the parts out of alignment.
Fit up and distortion control again. What about an incompletely filled groove? That sounds pretty straightforward, like there's just not enough weld metal deposited in the joint preparation.
Exactly that. An incompletely filled groove is basically a continuous or intermittent channel or depression left along the surface of the weld because not enough filler metal was deposited to completely fill the prepared joint groove up to the level of the surrounding parent metal.
How is that different from undercut? Both are grooves.
The key difference is location and effect. Undercut is a groove at the toe of the weld in the parent metal. An incompletely filled groove is in the main body of the weld face itself. While undercut primarily creates a stress concentration, an incompletely filled groove directly reduces the effective cross-sectional area, the throat thickness, of the weld. This directly impacts its load-bearing capacity.
Less metal to carry the load.
Precisely. It's typically due to simply not depositing enough weld metal, maybe not enough weld passes, or using poor welding technique that results in an irregular, concave, or underfilled weld bead surface.
Okay. Irregular width seems fairly self-explanatory. The weld bead varies excessively in its width along its length. What might cause that?
One common cause can be severe arc blow, where magnetic forces deflect the welding arc, causing it to wander side to side unpredictably, leading to fluctuations in bead width.
Magnetic interference.
Right. Also, inconsistent manipulation of the welding electrode or welding torch by the welder, maybe uneven travel speed or weaving pattern leading to an irregular weld bead surface, can obviously contribute to variations in width.
Is irregular width just cosmetic, or can it cause problems?
While it might not always critically compromise the basic structural integrity in the way a crack or lack of fusion does, it can have consequences. An inconsistent width means an inconsistent heat input along the length, which can affect the width and properties of the heat-affected zone. In certain materials, like high-strength, low-alloy, HSLA, steels where HAZ properties are critical, or in duplex stainless steels where the phase balance is sensitive to heat input, significant variations could potentially impact the local mechanical properties or corrosion resistance.
So consistency matters. Root concavity is another one that occurs on the backside, the root of a butt weld.
Yeah.
What's that?
Root concavity, sometimes called suckback, is a shallow groove or depression that forms along the center line of the root of a butt weld as the molten metal shrinks during solidification. It's kind of the opposite of excess root penetration.
Instead of bulging out, it sinks in.
Exactly. It can be caused by not using enough arc power or heat input to ensure a slightly positive convex root bead profile. Incorrect joint preparation or fit-up may be too tight a root gap or too thick a root face that doesn't adequately support the molten metal at the root can contribute.
Okay.
In TIG welding, using excessive pressure for the backing gas shield on the root side can actually push the molten metal back up, creating concavity. Poor welder technique Or if slag from the welding process flows into the groove of a temporary backing bar and prevents proper metal deposition right at the root, can also cause it.
How do you prevent it?
Ensuring sufficient arc energy, adhering strictly to the qualified welding procedure regarding joint preparation and fit-up, controlling backing gas pressure carefully, proper welder training, and sometimes adjusting the work angle slightly can all help. Using consumable inserts or permanent backing strips can also be effective in supporting the molten metal at the root and preventing excessive concavity.
Right. And finally, in this shape category, burn through that sounds like a pretty significant problem, a catastrophic failure during welding.
It is. Burn through is essentially when the molten weld pool becomes too large and fluid for the amount of supporting material underneath it, and it completely collapses, creating an open hole right through the joint. Molten metal might just fall away.
A hole instead of a weld. Not good.
Definitely not good. This is usually a result of welding parameters or technique being way off. Using an insufficient welding travel speed, going too slow, builds up too much heat. Applying too high a welding current for the material thickness and joint design is another major cause.
Too much heat, too slow.
Right. It can also stem from a lack of skill or coordination on the part of the welder, particularly on thin materials or root passes. Sometimes it's due to faulty joint preparation, excessively grinding the root face during prep, making it paper thin, or having a root gap that is simply too large for the welding process and settings being used. There's just not enough material there to support the pool.
And fixing it.
It's considered a gross imperfection and typically requires skilled repair. Often involves cutting out the damaged section entirely, maybe preparing the edges again, and then carefully re-welding, possibly using backing or different techniques to bridge the gap initially.
Okay, that's a really thorough look at the various ways a weld's shape and dimensions can deviate from the ideal. We've got one last main category to cover now: miscellaneous imperfections. What kind of issues fall into this final catch-all group?
Right, this is a bit of a grab bag for imperfections that don't neatly fit into the other 5 main categories we've discussed: cracks, cavities, inclusions, lack of fusion penetration, and imperfect show.
So what's a common one here?
One you see fairly often is stray arc or arc strike. This is localized damage to the surface of the parent metal caused by accidentally striking the welding arc outside of the intended weld groove or joint area.
Ouch! Like accidentally touching the electrode where you shouldn't.
Exactly. It leaves behind small, irregularly shaped areas of fused metal on the base material surface. The problem is that little spot has been rapidly heated and cooled, creating a potentially very hard and brittle heat-affected zone underneath it, which might even contain microcracks.
So it's not just cosmetic damage.
Definitely not. It can be a potential crack initiation site. Stray arcs can happen if you have limited physical access to the joint, making it hard to control the electrode, if the electrode holder or welding torch has faulty electrical insulation, if there's no properly insulated place provided to safely rest the electrode holder when you're not actively welding.
Carelessness, basically.
Sometimes, yes, or poor equipment maintenance. Also, if the work return clamp, the ground clamp, is loose or making poor contact, the current might arc at that connection point instead of flowing properly through the workpiece. Even adjusting the wire feed speed knob on some MIG welders without first isolating the welding power can potentially cause a brief arc strike if the torch trigger is accidentally activated.
What's the fix for an arc strike? Just grind it off.
Because of that potential for a hardened and cracked HAZ underneath, it's usually recommended to carefully grind out the entire affected area of a stray arc strike, making sure to remove the fused spot and any underlying heat-affected material. Then you'd typically perform some non-destructive testing, like magnetic particle or dye penetrant inspection, to ensure no cracks remain. Welding over it is generally discouraged, as you might just hide a crack.
Right. Better to remove it properly. What about spatter? Those little droplets of weld metal that stick to the area around the weld? Everyone who's seen welding has seen spatter.
Exactly. Spatter is formed when small globules of molten weld metal, or filler metal, are expelled violently from the welding arc and fly outwards, adhering to the surface of the base metal or previously deposited weld metal nearby.
What causes it? Is it just unavoidable?
It's often controllable to a large extent. Common causes include using too high a welding current, which makes the arc more forceful, or maintaining too long an arc length. Magnetic arc flow, which we mentioned earlier, can also cause erratic metal transfer and increased spatter.
Okay.
Incorrect voltage or inductance settings on GMAW MIG-MAG welding machines can significantly affect the metal transfer mode and lead to spatter. Using welding electrodes that have absorbed moisture can cause gas evolution that ejects metal droplets, and using a shielding gas that isn't appropriate for the specific application or material, like using pure CO2 for spray transfer in MIG, can also lead to excessive spatter.
So it's often a sign that things aren't quite optimized.
Generally, yes. While spatter itself is often considered more of a cosmetic imperfection, although heavy spatter can be time-consuming to remove its presence, especially if excessive, usually indicates that the welding parameters or conditions aren't quite ideal. There might be other underlying issues, like unstable arc or excessive heat input that are also occurring.
Can you do anything to make it easier to remove?
Yes, welders often use anti-spatter compounds. These are typically liquids or sprays applied to the base metal surface around the weld joint before welding. They help prevent the spatter droplets from adhering strongly, making them much easier to brush or wipe off afterwards.
Okay. What about a torn surface? That sounds like damage from removing something.
It is. A torn surface is damage that occurs on the base metal when temporary welded attachments, things like lifting lugs used during fabrication or small tabs used for fit-up alignment, are removed improperly. Instead of being carefully cut off and ground smooth, they might be knocked off with a hammer, fracturing them away from the base plate.
Leaving a rust-jagged area.
Exactly. This can leave behind a rough, fractured surface on the parent metal that definitely needs attention. It needs to be ground smooth to remove the stress risers, and then it should be inspected carefully, usually with NDE, for any cracks that might have initiated during the tearing process. Depending on the criticality of the application and the relevant welding standards, a weld repair might also be required in these areas to restore the surface, although in some structural codes, any welding on these torn zones might be restricted due to the potential for underlying damage.
Right. Care needed when removing temporary bits. And what else might fall into this miscellaneous category? Any other examples?
Sure. You might encounter things like grinding marks, which are localized areas of damage or material removal caused by careless or excessive use of a grinding tool, maybe leaving deep scratches. Chipping marks can be left behind from using a chipping hammer or other hand tools too aggressively to remove weld spatter or slag. Underflushing is a term sometimes used when too much material has been inadvertently removed by grinding, maybe when trying to smooth the weld cap, actually reducing the thickness of the weld or the parent metal below its required dimension.
Grinding too deep.
Right. Misalignment of opposite runs can occur specifically in double-sided MUT welds if the center lines of the two weld beads deposited from either side of the joint are not properly aligned with each other. And one more example, particularly relevant for stainless steels, is temper color or heat tint. This is a thin oxide film that can form on the surface of the stainless steel in the heat-affected zone during welding due to the heat. While often just cosmetic, heavy heat tint can sometimes indicate excessive heat input and potentially affect the corrosion resistance in that area if not removed.
That's a remarkably comprehensive overview of all the different types of welding imperfections we might encounter. It really highlights just how many factors, from material prep to technique to parameters, can influence the final quality of a weld.
It does indeed. It's a complex interplay. And being able to accurately identify these different imperfections, understand their likely root causes, and know how to implement effective preventative measures is absolutely essential for anyone involved in welding to ensure the long-term structural integrity, safety, and reliability of welded structures and components.
Yeah, absolutely. And I know that just spotting one of these imperfections doesn't automatically mean the entire weld is scrap, right? There are acceptance criteria and quality standards that come into play to decide if it's okay or not.
Yes, exactly. That's a critical point. Welding acceptance standards, which are usually defined by industry codes like ASME or AWS or European standards or specific project specifications, define the allowable limits for various types and sizes of imperfections based on the application, the material, the loading conditions, and the required service life.
So a tiny bit of porosity might be acceptable in one situation but not another.
Precisely. The standards provide criteria, maximum size, length, frequency, distribution for imperfections like porosity, slag inclusions, undercut, excess reinforcement, etc. It's important to remember, though, that certain types of imperfections, most notably cracks of any size, are almost universally rejected across all critical applications. Their potential to propagate under stress is just too high a risk.
Right. Cracks are generally a no-go.
Pretty much. But for many other types of imperfections, the acceptability will depend entirely on comparing what's found during inspection against the specific acceptance criteria outlined in the governing standard or specification for that particular job.
So let's say an inspection, maybe visual, maybe radiographic, maybe ultrasonic, reveals an imperfection that does exceed those allowable limits. It's deemed a defect. What's the typical next step then?
Well, typically the unacceptable imperfection, the defect, needs to be rectified. It needs to be repaired. For relatively minor surface imperfections, like shallow undercut or maybe excess reinforcement, sometimes a simple dressing of the weld by careful grinding might be sufficient to bring it within tolerance.
Just smooth it out.
Right. However, for more significant defects that penetrate into the weld metal or the heat-affected zone, things like deep cracks, significant lack of fusion, extensive slag inclusions, or burn through the flawed material will usually need to be completely removed,
How do they remove it?
often by mechanical means like grinding, or sometimes using thermal methods like arc gouging, which uses a carbon electrode and compressed air to melt and blow away the defective metal. The excavation needs to be carefully shaped and cleaned.
And then re-weld it.
Exactly. Once the defect is fully removed and the area is properly prepared, it needs to be re-welded. Crucially, this repair welding must be done following a qualified and approved welding procedure, often the same one used for the original weld, or sometimes a specific repair procedure. The welder doing the repair also needs to be qualified.
So it's not just a quick patch-up job.
Not at all, especially in critical applications. The level of scrutiny and inspection required for the repair weld itself will depend on the criticality of the original weld and the requirements of the applicable standards. The repaired area will typically be re-inspected using the original NDE method to ensure the defect has been successfully removed and the repair is sound.
It really brings it all back around, doesn't it?
Yeah.
To the fundamental importance of having skilled and knowledgeable welders in the first place, adhering strictly to sound, qualified welding procedures, and conducting thorough quality control and inspection throughout the process to minimize these issues occurring.
Absolutely. Prevention is always better than cure, especially in welding. Minimizing the occurrence of welding imperfections relies so heavily on having well-trained, conscientious welding personnel who understand the why behind the procedures, who diligently follow those established procedures, and who appreciate the critical importance of each step from material handling and preparation through parameter control during welding to inter-run cleaning.
And the inspection side.
And of course, the role of qualified welding inspectors using the appropriate non-destructive testing methods correctly is absolutely vital for identifying any imperfections that do inevitably occur, and then ensuring that they are properly evaluated against the relevant acceptance criteria and addressed appropriately if necessary. It's a team effort to ensure quality.
It's clear that achieving a consistently sound weld is a really multifaceted process, requiring skill, knowledge, and diligence at every stage. And having this deep understanding of all these potential imperfections and their causes is absolutely key to creating welded structures that you can trust to be both reliable and safe. Thanks so much for this incredibly detailed deep dive into the sometimes hidden world of welding imperfections.
My pleasure. It's a complex topic, but definitely an essential aspect of engineering and manufacturing that's worth understanding.
And that brings us to the conclusion of this deep dive. Perhaps the next time you encounter a welded joint, whether it's on a bridge, a building, a pipeline, or even just some metal furniture, take a moment to appreciate the intricate processes and the potential challenges involved in creating that seemingly simple connection. As we've heard, there's a whole world of potential imperfections, and the expertise required to prevent or manage them, hidden just beneath the surface. Something to think about. Until our next exploration.